So yesterday we started talking about graphing polar functions. Okay. We saw how using a table can be really helpful as we piece through plotting the points. Okay. We also saw how if we look at the XY graph, that can be helpful as we distinguish different points there are different properties that we can see. We will still be talking about the graphs when we do topic 15 on Friday and on Monday. That and it's like cool. We're ending content the same way we began content with rates of change. So we're going to be able to talk about the rates of change of a trig function and how it relates to the graph, which is pretty cool. So, all right. So we did example 1, we did example 2. So let's dive into example 3. So in example 3 is going to be different because example 3, we are going to be talking about graphing the polar function on an odd looking interval. Okay. This problem was inspired. I put in. This is inspired by questions you can see on AP Classroom. Okay. And even some things that we can see in topic 15 a little bit. So we're going to graph the polar function r of theta equals 2 cosine of 2 theta on the domain of negative pi over 2 to pi over 2 on the polar coordinate system. Now, one thing that we're going to do as well is sometimes graphing it in the xy plane is going to help us. It's equivalent to making a table, okay? But when we look at functions like, if we look at functions like this, there are two things I can recognize. Number one, I have a horizontal dilation and a vertical dilation. Okay, so I can bring that stuff with me in from like topic 6 to help me graph this, just like essentially from memory, because I know that cosine, it's 1, 0, negative 1, 0, then 1. The 2 condenses the graph so that my 1 period will look like this. Oops. Let's do green today. 2, 0, negative 2, 0, 2. Okay. I will also say, just because of the nature of this class and like the SAT, you'll never see something this hard on the SAT. Because that's the SAT really, there's some like geometry and stuff in there. But like, so now that's from 0 to pi. I'm going to go now in the other direction. The pattern is the same. Okay. Cosine is a even function. A even function is a function that reflects over the y-axis. Okay, I'm going to write that up here. Y-axis reflection is an even function. Okay. Another example of an even function is x squared. You fold it in half, it's exactly the same. Now, I think, it's done. I think one reason that this is helpful, drawing this graph, is that it can help me recognize what points I'm going to plot on the polar graph. Okay, so we're just doing from negative pi over 2 to pi over 2. So let's write out what each of these points are in the polar graph. Now in the polar graph, we plug in the angle, we get out the radius. But then the radius is the first thing that we deal with. So this polar point right here would be negative 2 comma negative pi over 2. Okay, let's graph that point first. Okay, so yeah, it does split. It is a little bit different that way. So negative 2, negative pi over 2. I'm going to go out to 2. Negative pi over 2 would be down here, but then now I reflect across. Okay, so that is negative 2, negative pi over 2. The next point that we could graph, okay, it's going to do a little mental math here. Actually, let's do these 5 points, and then we're going to fill in some points in between. So the next point would be 0 comma negative pi over 4. So that point would be, the radius is 0. So this is a point at the origin. I'm not going to connect the dots quite yet. Next, the next point is 2 comma 0. 2 comma 0 is right here. Okay, it's a radius of 2, the angle is 0, so it doesn't move at all. Next point, oh, it's 0 comma pi over 4. I'm back at the origin. Okay. The next, and then the last point is going to be negative 2 comma pi over 2. So 2 pi over 2 reflected across. So that point is all the way down there. So so 0 negative pi over 4, 0 pi over 4 are the same point. Now, here is why maybe a table could be an advantage. There is some more information that I could use in here to find a few more points. Okay, you might recall that between negative pi over 2, sorry, I'll do this. Between 0 and pi over 4 and pi over 4 to pi over 2, we do have pi over 6 and pi over 3. Okay, so equivalently, we would have a value over here at negative pi over 6 and negative pi over 3. Just for simplicity's sake, I'm going to use my calculator because I don't want to get that. So, in the calculator, 2 cosine 2 times negative pi over, I'm going to do pi over 3 first. Okay. That value is at negative 1. So this point right here is negative 1 comma negative pi over 3. Okay. So I'm going to plot that point right here. So radius of 1, negative pi over 3 is right here. Then it is reflected across. Okay. Then at 2 times cosine of 2 times negative pi over 6, that is 1. So that value is right there. This is 1 comma negative pi over 6. So that point, oh, these are so cool. This is going to help you with like homework and stuff like that. Radius of 1, negative pi over 6, is right here. Okay, so if we track these points as I connect them, -2, comma, negative pi over 2 was right here. Then we went right there with that next point, then 0, negative pi over 4, and then 1, comma, negative pi over 6. Okay, and then the next point was 2, 0, which is right there. Okay, so then now that I have those negative angles, I know what the positive angles are as well. At the value of 1, I had an angle at pi over 6. Okay, so 1 pi over 6 is right here. So the graph then looks like that. Okay, then 0 pi over 4 was right there. And then down beneath here, at -1, I have a value at pi over 3. Okay. 2 cosine 2 times pi over 3, -1. So then that value, radius of 1, angle pi over 3 reflected across. Boom, boom. That is a polar graph. Now, this is a polar graph that is not complete. Okay. If we had, so it's clear that this is only one cycle. So this is actually only half of the graph, half of what the graph would actually look like. Here is something neat. I'm going to use the blue here for a second. If we did like from pi over 2 to pi, and then the next piece, here's what the rest of the graph would look like if we graphed the whole picture. So we started up here, we looped through the origin, we looped out to 2, we started coming back through the origin, back down. That's what the rest of the picture would look like. If we graphed more points. Okay. Now, we will learn this later. What does that kind of look like? Ooh, man, it is a flower. As I was saying that, I was like, oh, they could probably say like, oh, it looks like a propeller. This is called a rose curve. Because if you think about a flower with roses, what do you think about it? Okay, now, here's number 2. The 2 on the outside. The furthest out point is 2, 0, 0, 2, -2, 0, 0, -2. What do you think the 2 on the inside has to deal with? Yes. What do you mean by that, though? So that's what the 2 in the front is. What do flowers have? Yep. 2 times 2 gives you 4. If it was odd, if that was a 3, there would only be 3 petals. Just because of how the graph works. And that flower would actually look a little bit different. Now, here are a few things worth pointing out. On the AP exam, you don't need to know the names of these polar functions. I'll teach you what they are. That's what we're doing kind of in this second portion. But yeah, you don't need to know what the names actually are. Okay. So let's tally ho. All right, so all of these polar curves, all these polar functions, they have different names. Example 1 was a circle. We recognized that yesterday. So all of your circles, I'm going to do a highlighter. All of your circles are going to look like this. Okay? They're going to be r of theta equals either a. So I think if it was r equals a, that would just be like a circle centered around the origin. But a sine of theta and a cosine of theta, they are circles that lie on the different axes. So like yesterday, we did, was it 4 cosine? I think it was 4 cosine. And that circle was along the positive x-axis. So for sine of theta, let's do it. Yeah, let's keep it. So if we look at 4 sine of theta, 1, 2, 3, 1, 2, 3, 4. 4 sine of theta would be on the positive y-axis. Like that. That is our circle. I just can't draw them. Okay. Where do you think -3 cosine of theta would be? Where do you think -3 cosine theta would be? Good. 1, 2, 3. Good. And then -2 sine theta would be right there. Awesome. Okay. So these are circles. We will see circles in lesson 15 as well. Okay. In example 2, when the graph of 2 minus 4 cosine of theta, these are called limachones. Okay. The French word for snail. Don't ask me why. That's just what they're called. Now, when the numbers are equal, they're called a cardioid. What do you think about when you hear cardioid? Yes. So when the numbers are equal, it's more of a shape. It's more of a heart-shaped figure. And here's the other thing. Cardioids don't have that inner loop like limachones do. Okay. So don't we have a fourth example? Oh yes, we do. Okay. All right. So here are some limachones. Some limachones have the inner loop. Some have a dimple. The dimple is like the cardioid part. So 3 minus 3 sine of theta. This is going to go out to 6, and it's going to open down. So this one looks like this. I believe it goes up 3 here, 3. It will look like that, roughly. Okay. So that's what they mean by the dimple. It'll like dip down and then come back up. -2 plus 3 sine of theta I have it. Oh, I don't have it. I think I skipped over this last year, or at least this point. Polar y equals -2 plus 3 sine of theta. I'm thinking that the 3 is going to open up, but I'm forgetting what the -2 is going to do. It's probably going to make the inner circle a little bit smaller. It's probably going to be at 1. I'm just talking to myself. That comes all of this. Okay, graph. Yes, okay. So the value is going to be out at 5. 1, 2, 3, 4, 5. There's a point at 0, 1. And then there's a point at -2 and +2 on the x-axis. So when I trace this, this starts at this point, comes out, comes back in, comes back out, goes all the way around like that. So this value is 5. That's coming from 2 plus 3. This value here is is 1. And that's because you're doing -2 plus 3. And these values are 2 and -2. And that's coming from the 2p. If I change that to a -3, yes, if I change that to a -3, this would be a cardioid, and the point would be at 3 and not -2. And then, now, so why don't you give the third one a go? I'm going to stand in front of what I'm going to do, and then we'll check our answers. Oh, oops, no. Oh, oops. Oh, all right. That's what I did. That's not right. Yes. I'm partially right. There's no inner loop. 3. So -2 plus 3 gave me that 1. That 3 minus 3 gave me 0. 3 minus 2 is +1. So the point is right here. Oops. The point is right here. So it looks like that. Yep. Looks like that. But it's still out at 5.
I put no loop in there because I thought you always had a loop.
Yes. So this is a little bit different. All right. All right. Okay. So Lee-Michon's is one. Rose curves are another. Okay. Now I feel like now we're just being a little repetitive, but it's okay. So this one, 4 sine of 2 theta. Let's go ahead so that I don't have to stop the video. 4 sine of 2 theta. So there are a few things that I can hypothesize about this one when I have, knowing that I've seen the rose curve from before. Now, one thing that's important to recognize is that when you saw the rose curve up here, you will notice that the cosine, the petals are on each of the axes. But what's important to also recognize is that why would we have the same graph if we changed it to sine? Sine, it looks a little bit different. The 2 on the inside, they're still going to be 4 petals, okay? But these petals are going to go in between each quadrant. Now, let's think about why that is for a second. The reason, so what really, when we think about sine and cosine, what did we call them back in, like, when we looked at the unit circle? What did we call them? Go ahead.
Sinusoidal function.
They are sinusoidal functions. That's not quite what we're looking for, though. They are complementary. They're co-functions. The only difference between sine and cosine is that 90 degrees. So, because of how it works here, that 90 degrees, because of the dilation, gets cut in half. So sine graphs, if we think about cosine, sine graphs are just a rotation of the cosine graphs, or the other way around. So these are going to look like this. I'm going to go out to 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. 1, 2, 3, 4. Okay. So these graphs, I'm trying to think about where it is important to think about where it starts. Okay. Especially when we get to topic 15. So if I plug in angle 0, because that's the first angle, okay. If I plug in 0, sine 4 sine of 0 is 0. So it starts at the origin. My next value would be pi over 2. Sine of pi over 2 would be sine of pi. Sine of pi is 0. Sine of pi is, oh, I should be doing pi over 2. Pi over 2 is the next one, the next key point. Sorry. So it'd be 4 sine of 2 times pi over 2. Well, that is 4 sine of pi over 4. Why is that sounding right? 2 times pi over 2 is pi. Sine of pi is 0 still. So I want to do pi. Oh, I want to do pi over 4. If I plug in pi over 4, no, then that gives me, yeah, that'll give me pi over 2. Sine of pi over 2 is 1. 4 times 1 is 4. So we're starting here, and we are going out to there.
How do we know where to put the curve? Like, do we guesstimate?
Yes. Yep. And then it comes back. Okay. So like this would be the graph if I did from 0 to pi over 2. Okay, we're tracing our way through the XY. That's why this is why the XY graph can be really helpful. I know it says use the calculator, but I wanted us to see how we do this without it. And then if we do, so we've done pi over 4, pi over 2, 3 pi over 4, 3 pi over 4 times 2 would be 6 pi over 4, which would be 3 pi over 2. Sine of 3 pi over 2 is negative 1. 4 times negative 1 is negative 4. So radius of 4, 3 pi over 4 reflected across. There's the next pedal. There it is. The reason I know that this second quadrant is the last quadrant is because I'm dealing with large angles and negative radiuses. So I do the radius, the large angle, then I reflect it across. And so when you put this in the calculator for sine 2 theta and you do the trace, when you press trace and you do the arrows, it follows the pattern of the graph. Okay? So first quadrant, fourth quadrant, third quadrant, second quadrant. Okay? So, all right, up here, we went from the first quadrant to the fourth quadrant to the third quadrant to the second quadrant. Okay? So, again, I'm always trying to show you how can we do these problems without the calculator because, oh, I'll be able to tell this. I'll be able to tell you this from this. So on last year's exam, so on last year's exam, there are 15 calculator active questions. Out of the 15, they really only needed the calculator on 6 of them, where you had to use the calculator. Okay, so that was this. That's like differential equations. That's not. Okay, there we go. There are 12 calculator active questions. You had to use the calculator on only 5 of them. So 5 of the 12, you had to use the calculator. So there were 35 questions between the calculator and non-calculator parts where you do not use the calculator. Okay. So using the calculator is absolutely very important. Good to check answers, but you don't always have to do it or have to use it.
Okay. Flowers on my calculator.
Oh yes. So like if we had like 6 inside, there would be 12 petals. So this is where we're going to summarize this last part. So these are called rose curves. Okay, they look like A sine B theta and R equals A cosine of theta. Okay, rose curves produce roses. Okay, so when we look at these other ones, these rose curves will look like this. For cosine of theta, for cosine 2 theta, is going to go out to 4, and it's going to go out to 4, and there are going to be 4 petals. Not my best. 2 sine of 3 theta. I'm just going to double check. I think I remember what these look like. These ones look like 2 sine of 3 theta. Look like this. Look like that. Okay. And then for cosine fourth, they're going to be 8. Oh boy. For cosine fourth,
How did you do that? Did you do that?
3 petals. It goes. It should only go out to 2.
Oh, okay. Do you just put the 2 of them at pi over 4?
Hmm?
You just put 2 of them at like pi over 4?
Yeah. Oh boy. That's how we do 8. Okay, here we go. 1, 2, 3, 4, 5, 6, 7. Oh, I missed one right here. 8. Okay. 8. Looks like a squid or an octopus. Kind of. Wait. How many tentacles do octopus have? They do have 8. And spiders have 8 legs. Alright, so, alrighty. With this, you should be able to do the rest of the graphs on the homework. I'm okay with you using the graphs on the calculator to check your answers. Okay? So, alrighty. I hope you all have a good rest of your day.